Welcome. For millennia, humanity has looked to the stars and wondered, are we alone? But in the 21st century, that question has evolved. We now ask, where do we go next? For many, the answer is a small reddish dot in our night sky, Mars. This is the story of Mars colonization, not a distant science fiction fantasy, but a tangible goal being actively pursued by the brightest minds of our generation. Over the next 50 minutes, we will journey from the launch pads of Earth to the crimson deserts of Mars. We'll explore the groundbreaking technology making this possible, the monumental challenges that lie ahead, and the realistic prospects for humanity becoming a multi-planetary species. This is the blueprint for our second home. The dream of Mars is not new. It has captivated our imagination for over a century. Early astronomers saw what they believed were canals, sparking visions of a dying civilization. While we now know these were optical illusions, the idea of Mars as a potential abode for life persisted. Today, the motivation is more urgent. A single-planet species is vulnerable. Asteroid impacts, pandemics, climate change, these are existential threats. Establishing a self-sustaining outpost on another world is the ultimate insurance policy. It's about securing the long-term survival of human consciousness. But why Mars? Of all the planets in our solar system, Mars is the most Earth-like. A Martian day, or sol, is just 39 minutes longer than an Earth day. It has polar ice caps, a thin atmosphere, and a varied geology with canyons, volcanoes, and ancient riverbeds. It is a world that once had liquid water on its surface. While it is now a cold, desolate desert, the raw materials for a new civilization are there, waiting to be unlocked. The journey to Mars is being led by a new generation of pioneers. At the forefront is SpaceX, led by Elon Musk. Their vision is bold and uncompromising: to build a city of 1 million people on Mars. The key to this vision is a revolutionary vehicle, Starship. It is the largest and most powerful rocket ever conceived. Standing 120 meters tall, Starship is designed to be fully and rapidly reusable. This is the critical innovation that changes the economics of space travel. In the past, rockets were thrown away after a single use, making spaceflight incredibly expensive. By creating a reusable transport system, SpaceX aims to lower the cost of reaching orbit and Mars by orders of magnitude. The Starship system consists of two parts: the Super Heavy booster, which provides the initial thrust to leave Earth's atmosphere, and the Starship spacecraft itself, which will carry up to 100 people on the long journey to Mars. SpaceX's plan involves launching a fleet of Starships. Some will carry people, others will be tankers that refuel the crewed ships in Earth orbit before they begin their interplanetary voyage. It's a logistical ballet on a cosmic scale. While early timelines were incredibly ambitious, recent progress and testing in 2024 and 2025 show a clear, if challenging, path forward. The goal is to land the first uncrewed Starships on Mars by the late 2020s to deliver cargo and prepare for the first human arrivals around 2030, or shortly thereafter. But this endeavor is not a one-company race. NASA, with its decades of experience, is pursuing a methodical, science-driven approach known as Moon to Mars. The logic is simple: learn to live and work on a nearby celestial body before attempting the far more difficult journey to Mars. NASA's Artemis program is the proving ground. By establishing a sustained human presence on the Moon, NASA will test the technologies essential for Mars. This includes new deep space habitats, advanced life support systems, surface power generation, and experience with extravehicular activities in a hostile environment. The Space Launch System, or SLS rocket, and the Orion crew capsule are the foundational hardware for these missions. NASA is also a key partner for commercial companies funding the development of lunar landers, including a version of SpaceX's Starship, to ferry astronauts to the lunar surface. Every step taken on the Moon is a dress rehearsal for the first human footprints on Mars, which NASA currently targets for the late 2030s or early 2040s. Other nations are also looking toward Mars. China has successfully landed its Zhurong rover on the planet and has publicly stated its long-term goal of sending crewed missions. The European Space Agency, ESA, continues its vital contributions with missions like the ExoMars program. The colonization of Mars will likely be a global effort, combining the resources and expertise of multiple space agencies and private enterprises. The voyage from Earth to Mars is a monumental undertaking in itself. It is a journey of approximately 225 million kilometers on average, lasting 6 to 9 months. The timing of this journey is dictated by celestial mechanics. Launch windows open roughly every 26 months when Earth and Mars are in the optimal alignment, allowing for the most fuel-efficient trajectory, known as a Hohmann transfer orbit. Missing this window means waiting another 2 years. Once a spacecraft leaves Earth's protective magnetic field, its crew is exposed to the harsh environment of deep space. The two greatest dangers are galactic cosmic rays, or GCRS, and solar particle events. GCRs are high-energy particles from distant supernovae, and they are a constant, pervasive source of radiation. Solar particle events are unpredictable bursts of radiation from our own sun. This radiation can damage human DNA, increasing the long-term risk of cancer and other health issues. Shielding is therefore critical. Spacecraft will need specially designed hulls, potentially incorporating layers of water or hydrogen-rich materials which are effective at blocking these particles. The crew quarters, or storm shelters, will be the most heavily shielded areas, where astronauts will retreat during a solar storm. Then there is the challenge of microgravity. Living for months without the pull of gravity takes a severe toll on the human body. Bones lose density, muscles atrophy, and the cardiovascular system weakens. To combat this, astronauts on the International Space Station follow a rigorous exercise regimen for 2 hours every day. For a Mars mission, advanced exercise equipment will be essential. Scientists are also exploring concepts for artificial gravity, where a section of the spacecraft would rotate to simulate a gravitational pull, though this presents its own significant engineering challenges. Beyond the physical, there is the psychological toll. A small crew, confined to a small space for months on end, with Earth shrinking to a distant blue dot. The communication delay with Earth will grow from minutes to over 20 minutes each way, making real-time conversation impossible. Autonomy, resilience, and crew cohesion will be paramount. Missions like the HISEAS experiment, which simulate Mars missions in remote locations on Earth, are providing crucial data on the psychological factors needed for a successful crew. After months of travel, the most critical phase begins: entry, descent, and landing. Mars's atmosphere is too thin to rely on parachutes alone, but thick enough to create immense friction and heat. It's a phase often called the 7 minutes of terror. For a massive vehicle like Starship, this will require a complex series of aerodynamic maneuvers, using its fins to control its descent before reigniting its engines for a powered vertical landing. The first humans on Mars will be explorers, but more importantly, they will be construction workers. Their first priority will be to establish a permanent, pressurized habitat. Initial habitats will likely be prefabricated structures brought from Earth, or perhaps inflatable modules that can be expanded on site. But for a colony to be sustainable, it cannot rely on Earth for everything. The key to long-term survival is living off the land, a concept known as in situ resource utilization, or ISRU. Mars, though barren, is rich in resources. The most critical resource is water. We know from orbital and rover missions that vast quantities of water ice are frozen in the soil and at the polar caps. Robotic miners will be deployed to excavate this ice. Once melted, the water can be used for drinking, sanitation, and for irrigating crops in greenhouses. But its most important use is as a source of breathable air and rocket fuel. Through a process called electrolysis, water molecules can be split into hydrogen and oxygen. The oxygen is for breathing. This is a game changer. An experiment on NASA's Perseverance rover, called MOXIE, has already proven that it can reliably generate oxygen directly from the carbon dioxide in Mars's thin atmosphere. This technology, when scaled up, will mean that colonists can produce their own breathable air. The hydrogen from water combined with carbon from the Martian atmosphere can be used to create methane fuel and oxygen oxidizer through the Sabatier reaction. This means that Starship, after landing on Mars, can be refueled using local Martian resources for its return trip to Earth. This is the linchpin of the entire colonization architecture. Without ISRU, a self-sustaining colony is impossible. Power will be another immediate necessity. Solar panels will be crucial, but Mars is farther from the sun and plagued by giant dust storms that can last for weeks, blocking sunlight. Therefore, nuclear power is seen as an essential component. NASA has been developing compact fission reactors like the Kilopower project, designed to provide steady, reliable power regardless of the weather or time of day. Shelter will evolve over time. Early habitats will give way to more permanent structures. Scientists are developing techniques to 3D print buildings using Martian regolith, the loose soil and rock on the surface mixed with a binding agent. This would allow for the construction of large, radiation-shielded habitats without having to ship heavy building materials from Earth. Another promising idea is to locate bases within natural Martian lava tubes, subterranean caves left by ancient volcanic activity that would provide excellent natural protection from radiation and micrometeorites. The vision is inspiring, but the challenges are immense, and we must approach them with clear-eyed realism. The Martian environment is relentlessly hostile to human life. The surface radiation level is significantly higher than on Earth, even with shielding. Long-term exposure remains a major health concern. The Martian dust is another problem. It is fine as flour, abrasive, and potentially toxic due to the presence of perchlorate salts. It will cling to everything, threatening to clog equipment and posing a health risk if inhaled. The low Martian gravity, about 38% of Earth's, is a great unknown. While it might make moving around feel easier, the long-term effects on the human body, particularly for those born and raised on Mars, are completely unknown. Will it affect bone development, organ function, or reproduction? These are questions we can only answer by going there. Then there is the challenge of agriculture. The Martian soil lacks the organic compounds needed for plants to grow. Early farming will take place in enclosed hydroponic or aeroponic bays under artificial lighting. Reclaiming and detoxifying the Martian regolith to create fertile soil will be a multi-generational project. And perhaps the greatest challenge of all is the sheer complexity and cost. A single failed component, a single software bug, can lead to catastrophe millions of miles from any hope of rescue. The cost of the Apollo program was immense. The cost of a sustained Mars colonization effort will be in the trillions of dollars. It will require sustained political will and economic investment over many decades, far beyond the typical cycles of governments and corporations. Because of these monumental difficulties, timelines have often been revised. The optimistic projections of the early 2000s have given way to more sober assessments. While a human landing in the 2030s is still a credible goal, the establishment of a truly self-sustaining city is likely a half-century away or more. It will be a process of slow, incremental growth, with the colony remaining fragile and dependent on Earth for many decades. So what is the end goal? What does a mature Martian society look like? In the long term, the most ambitious goal is terraforming, the process of engineering the Martian environment to be more Earth-like. This is the stuff of science fiction, but it is based on real scientific principles. The idea would be to thicken the atmosphere and warm the planet by releasing the vast amounts of frozen carbon dioxide in the polar caps and soil. This could be done theoretically by building factories to pump out powerful greenhouse gases or by placing giant mirrors in orbit to heat the surface. If successful, over centuries, the atmospheric pressure would rise. Liquid water could once again flow on the surface. Eventually, the planet could become warm enough to grow plants in the open. Creating a breathable atmosphere with sufficient oxygen would be the final and most difficult step, likely taking millennia. Terraforming is a project of almost unimaginable scale and raises profound ethical questions. Do we have the right to fundamentally change another world? What if Mars harbors its own microbial life? This is a critical question. Recent discoveries have hinted at the possibility of past or even present microbial life beneath the Martian surface. Planetary protection protocols are therefore strict to ensure we don't contaminate Mars with Earth life and that we don't bring anything dangerous back. The first Martians will not live on a green world. They will live in domes and subterranean cities. They will be scientists, engineers, and farmers, their lives dedicated to the survival and growth of their small, isolated community. A new culture will emerge, shaped by the harsh realities and profound beauty of their new home. The journey to Mars is the most audacious project humanity has ever attempted. It will test the limits of our technology, our finances, and our spirit. There will be setbacks and there will be tragedies, but the drive to explore, to push beyond the horizon, is etched into our DNA. Mars is not a backup planet. It is a second chance, a chance to build a new branch of human civilization, to expand our horizons, and to safeguard the flame of consciousness for eons to come. The first steps are being taken today. The journey has begun.